In this video, I will walk you through free response question number 1 from the 2018 AP Calculus exam. This problem is an accumulation problem involving an escalator, so we will be working with integrals. This is a calculator active problem, so we will be using our graphing calculator to the fullest extent. People enter a line for an escalator at a rate modeled by the function r given by this, where r at t is measured in people per second and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. There are 20 people in line at time t equals 0. Part A. How many people enter the line for the escalator during the time interval from 0 to 300? We have learned that the integral of a rate from a to b gives you the net change in amount from a to b. And that's exactly what they are asking us to find. When they say how many people enter the line between 0 and 300 seconds, they're asking us for the net change in the amount of people between 0 and 300. So to find this, we need to find the integral of the rate of change of people. And that's exactly what r at t is. R at t, measured in peoples per second, is the rate of change of people entering the line. So we just need to calculate the integral of r of t from 0 to 300 to find out how many people entered the line between time 0 and 300 seconds. This will be easy to do because this is a calculator active problem. So let's hit y equals and type r of t in for y1. R of t equals 44 times t divided by 100 to the third power times 1 minus t divided by 300 to the seventh power. So we can just type all of that in like so. I'm using the x variable instead of t. Now we just need to evaluate the definite integral from 0 to 300. So back to the calculator. Let's quit our way out of this by hitting second quit. For the integral, we hit the math button and choose option 9. We are integrating from 0 to 300. And we want to integrate r of t. But remember, we typed r of t into y1. So we just need to get y1 in here. We do that by hitting the vars button, which stands for variables, switch over to the y variables tab, and just choose option number 1 for functions. And there's y1, just hit enter. So here we are integrating y1, which is really r of t. And put your dx on the end. And that's it. So 270 is the answer. Since this is the AP exam, let's write our answer as a sentence. 270 people enter the line during the time interval from 0 to 300. Part B. During the time interval from 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? Remember that in the setup of the problem, they gave us two different rates. They gave us a function for the rate at which people enter the line, and then they gave us a constant function for the rate at which people leave the line. The overall rate of change of the people in line will equal the rate in minus the rate out. The rate at which people enter the line is given by r at t. The rate at which people exit the line is a constant 0.7 people per second. The first fundamental theorem of calculus tells us that the end amount at b equals the initial amount at a plus the integral of the rate from a to b. In the context of this problem, the end amount will be the number of people in line at time t equals 300, and the initial amount will be the number of people in line at time t equals 0. The integral of the rate from a to b will be the integral from 0 to 300 of the overall rate of change of the people in line, which we just decided was r at t minus 0.7. In the setup of the problem, we were told that there are 20 people in line at time t equals 0. So the initial number of people in line is 20. This is a calculator active problem, so we can type this entire thing into the calculator. We start out by typing 20 plus. Now it's time for the integral. We hit the math button and choose option 9. We are integrating from 0 to 300, and we are integrating r at t minus 0.7. Remember that we typed r of t into y1 under the y equals button. So we don't need to type it in again. We can just hit vars and switch to y vars and choose option 1 for function and choose y1. So y1 is really r of t. And then we subtract 0.7. And we will put dx instead of dt. And that's it. Kabam! 80 people. There are 80 people in line at time t equals 300. Part C. For t greater than 300, what is the first time t that there are no people in line for the escalator? In Part B, we just found that there are 80 people in line at time t equals 300. According to the piecewise function in the setup, for t greater than 300, r at t is 0. In other words, for times greater than 300 seconds, no one is entering the line. That means the only change will be that people exit the line at the constant rate of 0.7 people per second. So for this time interval, the rate of change of people in line is simply equal to negative 0.7 people per second. Here comes the first fundamental theorem of calculus again. The end amount at b equals the initial amount at a plus the integral of the rate from a to b. Since we are looking for the time that there are no people in line for the escalator, the end amount that we are looking for is 0 people. So we will use 0 for the end amount. We know that there are 80 people in line at time t equals 300. So let's use 80 as the initial amount. Now, how about this integral? I'm going to integrate the rate, which is negative 0.7, a very simple function. But I'm going to integrate it from where to where. Our initial amount of 80 people is at time t equals 300. So that's going to be the start time. What about the end time? The end time is what we're looking for, the time when there will be 0 people. That's an unknown time, so let's just call it t equals x. So let's just put in x for the upper limit of integration. So what we have is an integral defined function. This is not a problem. We can just graph the right side of the equation and see where it equals 0. So let's type all of this as a function into our graphing calculator under y equals. So let's move down to y2, and we are going to type 80 plus this integral. So let's go 80 plus. For the integral, we do math 9, and we are integrating from 300 to x. So 300 to x. All right, it's an integral defined function, but your calculator can handle this. And in here, we have the simple function of negative 0.7. And we can just use x again, and that's fine. So let's graph this. Right now, we have 2 functions highlighted. We only want to graph the second one. So I'm going to come back here and get on the equal sign of y1 and hit enter. So I'm turning this off. So when I hit graph, I will only be graphing the second function. Before we hit graph, we should think about the window that we need to view this graph. The x values start at 300. We're talking about values that are greater than 300. So let's click on the window button, and for the x max, this is going to be bigger than 300. So we need to pick a number like 400, 500. Let's just pick 500. We can always adjust this later. For x min, remember we are staying bigger than 300. So we might as well just type in 300 for x min. What about the y values? Well, we are starting with a maximum of 80 people, and then it's decreasing and decreasing all the way down to 0. So for the y max, let's choose something bigger than 80. Maybe I'll just do 100. And we're going all the way down to 0, but let's leave a little space. Let's leave it at -10. So let's hit graph and see what we get. This red line represents the total number of people over time, and we want to find the time when the number of people is 0. There is a function for that, so we can just hit second trace, and we will choose 0. The calculator is asking for left bound, so just make sure that you are a little bit to the left of the x-intercept and hit enter. Now the calculator asks for a right bound. Move the pointer to the right of the x-intercept and hit enter. When the calculator asks for a guess, move the pointer right to about where you see the x-intercept, as close as you can, and hit enter. So this is the answer, 414.286 seconds. On the AP exam, they will accept 414.286 if you want to round, because the next number is a 7, or they will accept 414.285 if you just want to truncate and cut it off. The first time there are no people in line is at t equals 414.286. If you don't like graphing, perhaps you're uncomfortable adjusting the window and all that, you can solve this problem without graphing. We can simply treat this integral like a definite integral. So we would have 0 equals 80 plus, and to evaluate a definite integral, you find the antiderivative, which in this case would be negative 0.7 t, and then you evaluate that antiderivative using the limits of integration. So we will evaluate from 300 to x. And then, in order to do this, we find the value at the upper limit minus the value at the lower limit. So we would have 0 equals 80 plus. So here comes the value at the upper limit, which is x. So we will have negative 0.7x, and then minus the value at the lower limit. So that's going to be negative 0.7 times 300. So then we just have 0 equals 80 minus 0.7x. Minus a negative is addition. 0.7 times 300 is 210. Adding 80 plus 210, we get 290 minus 0.7x, all equal to 0. Adding 0.7x to both sides, we get 0.7x is equal to 290. Dividing both sides by 0.7, let's see, 290 divided by 0.7, we get 414.286, which is the same answer that we got the last time. Part D. For the interval from 0 to 300, at what time t is the number of people in line a minimum? To the nearest whole number, find the number of people in line at this time. Justify your answer. As soon as you see this keyword minimum, you know that we have to find the absolute minimum, which means we are going to have to make a candidates test. To do a candidates test, we will first need to find the critical values. First semester, we found critical values by setting the derivative equal to 0. Second semester, we will think of it as setting the rate equal to 0. In the context of this problem, the rate that we're talking about is the overall rate of change of people in line. And we previously found that to be r of t minus 0.7. That's the rate in minus the rate out. We can find the critical values by graphing this function and seeing where it equals 0. We are graphing, so that means hitting that y equals button. Let's go on down to y3. We want to graph r at t minus 0.7. But remember, we have r at t up here at y1. So I can just go ahead and get y1 in here by using the vars button again. So vars, yvars, function, y1. Okay, so this y1 is really the r of t function. And then we want to subtract 0.7. So this is really r of t minus 0.7. We want to graph this, but right now we have two graphs that are turned on. So I could either clear out the other functions because I'm done with them, or I can just hit enter and turn the other graphs off. So before I hit enter, let's think about what the window should be. First of all, we are only considering times between 0 and 300. So that is your x min and your x max right there. So let's see, x min will be 0, x max will be 300. How about the y min and y max? Well, this rate, we're talking about the number of people per second getting in line. So, this is going to be a small number. 5 people per second, 3 people per second, these will be small numbers. So let's set the y min and y max as pretty small numbers. Like maybe you could put 10 or 5. You can change it if you need to. We need to see where the graph is hitting 0. So I like to leave a little space underneath so we can see where it crosses over. So I think I'll put this at -5. Let's hit graph and see what we have. Okay. The critical values are where the rate equals 0. So I can see that the rate equals 0 in two places. Let's use the 0 function by hitting second trace and option number 2. The calculator is asking for a left bound. So let's move to the left of the first 0. And we hit enter. Now the calculator asks for a right bound. So let's move to the right of the 0 and hit enter. Now the calculator asks for a guess. So move right to about where the x-intercept is and hit enter. So this is the first critical number, 33.013. We are going to need to use this value later when we make the candidates test. So I would like to store this number in all of its decimal glory into a letter on my calculator. So what you do is quit your way out of here, type X and then hit the store button and pick which letter you want to store the value in. I'm going to just use letter A. So I am storing all of these decimals into the letter A. Let's go back to the graph. We can just hit second trace, I believe, and let's do that 0 function again. And the calculator is asking us for a left bound again. So let's shimmy on over closer to the second x-intercept, stay to the left, and hit enter. And then the calculator asks for a right bound, so move to the right of this x-intercept and hit enter. Calculator asks for a guess. Slide on back to right around where the x-intercept is and hit enter. So here is the second critical number, 166.575. Again, I would like to store this, so I'm going to quit my way out of here, and I will pick X, store, and I'm going to choose letter B this time. So there we go, 166.575. It's time to set up the candidates test. Remember, we are looking for the time t when the number of people in line is at a minimum. So the first column will be the times, which are candidates for the minimum number of people. These candidates will include the endpoints. Don't forget the endpoints, 0 and 300. So we will have 0 at the beginning, and we will have 300 at the end. In addition, we will have the critical values, which are 33.013. There are actually more decimals to that, but that's a good start. And 166.575. These are the candidates. We need some sort of a function that will give us the number of people at each one of these times. Once again, the first fundamental theorem of calculus tells us that the end amount will equal the initial amount plus the integral of the rate. In the setup, we were told that there are 20 people in line at time t equals 0. So that is the initial amount. So there's your initial amount of 20 people. How about the limits of integration? The initial amount of 20 people is at time t equals 0. So the lower limit of integration is definitely going to be 0. What about the upper limit of integration? The upper limit will change each time depending on the value of t. So I'm just going to put a t here for right now. What is the rate that we are integrating? Well, again, it's this right here, r of t minus 0.7, the overall rate of change of the number of people in line. I feel like we are supposed to use a different variable here, like x, for example, is the way I always see it done when I have an integral defined function, but then maybe I should put an x here as well. I'm not sure that it matters, but there you go. Let's use our graphing calculator to find the number of people at each of these times. We can simply type this entire expression into the calculator as a function. Hit y equals as we prepare to type in a new function. Let's go ahead and turn off the function that's on, highlight the equal sign and hit enter. We need to type in 20 plus the integral from 0 to x of r of t minus 0.7 dt. Let's see how much of that I can remember. So on y4, I'm typing in 20 plus, and then the integral. So we hit math, 9. And we're going from 0 to x. So I will do 0 and then x for my limits of integration. And then in here, we need r of t, and that is y1. So once again, I'm going to hit vars, go over to yvars, choose option number 1, and choose y1. All right, so that is r of t. and then we need minus 0.7. And we'll just do dx again. It doesn't matter. So this is our function. To evaluate this at the 4 different times, we want to look at the table. So hit second graph, and then now you're looking at a table. The way I have it set, I'm going to enter in values one at a time. Let me delete the one that's there. But I need to show you how to make that happen. Because if you hit second table, you're probably going to see just a bunch of values listed all the way down. So first I actually hit second window to get at the table set. And what's important is you want the independent variable to be set to ask, and the dependent is set to auto. All right, that will give you this nice feature that I'm showing you now. So back to second table. So I can type these in one at a time. So first I want the number of people at time 0. We know that there should be 20 people at time 0. That's given. But this is a nice way of checking to make sure the function is working. So we type in 0 and hit enter, and indeed we see the 20. So let's go ahead and record that. So we have 20 people at time 0. What about time 33.013? This is a rounded value, so it would be risky to type this in right now. But remember, I stored this value in letter A. So this comes in handy now because I can just hit alpha A, enter. So this is the answer, 3.803. Let's record that. 3.803 people, which is approximately 4 people. And next we need to do 166.575. If you wanted to risk it, you could type this in. You might get away with it, but it is safer to remember that we type the entire decimal into letter B. So I can just go down and put in letter B, alpha B. So I have 158.07. I really want 3 decimal place accuracy, so I'm going to highlight this and I get all the decimals. The third decimal was a 0 anyway, so it wouldn't have mattered, but now I know that. 158.070. And finally 300, which I will just type in, 300. So you can kind of see the entire candidates test shows up right here on your calculator if you use this technique. But anyway, the last value is 80. 80 people. The number of people in line is a minimum at t equals 33.013. In addition to finding the time when the number of people in line is a minimum, to the nearest whole number, we need to find the number of people in line at this time. They also want me to justify my answer. So the number of people in line is a minimum at t equals 33.013 when there are 4 people in line. See Candidates Test. And that is the end of this problem.